Okay, so question 4, and immediately we notice a graph, so that's going to come into play. We're going to have a quick look at the question. Moving air can be used to generate electricity using a wind turbine. So moving air, quite a weird term for, well, wind. Wind can be used to generate from a wind turbine. So let's draw ourselves a little wind turbine here. Here's my little wind turbine, just so I lock into my brain what I'm talking about. Figure 8 is a graph of kinetic energy. So here we've got kinetic energy against wind speed for a mass of moving air. Mass of moving air, so wind. And if we look here at slower wind speeds, doesn't have much kinetic energy, but as the wind speed increases, the amount of kinetic energy increases as well. But it's not a proportional relationship, it's not a straight line, so we can't use the term directly proportional because we've got a curve. So the amount of increase is increasing as it gets higher and higher there. So just before the air reaches a wind turbine, it has a wind speed of 15 meters per second. So the air going in here is going at 15 meters per second. When the air has gone through, it has a wind speed of 13 meters per second. So let's add that in there, 13 meters per second. So we've got a drop of 2 meters per second. As the air moves through the turbine, some of its kinetic energy is transferred to the turbine. So we can see here it's going to have less kinetic energy because it's going slower. That kinetic energy has been transferred to the turbine itself, which is going to be used to turn a generator, which generates electricity. So here we go, use the graph. That's the real key thing for us. We've got to use the graph. You've got a question that says use the graph, guess what you've got to do? You've got to use the graph to determine the percentage of the kinetic energy transferred to the wind turbine from the air. So with this question, the first task is to think about the kinetic energy. So let's have a look. What do we know about the kinetic energy, or how are we going to find that out? Well, the key is these two bits of information here. It goes in at 15. So if I use this graph and have a look at 15 meters per second, I'm going to just grab my Luton Town pencil case, held together an elastic band, and let's get out my Luton Town ruler and a pencil to have a look at this graph then. So we're starting off at 15 meters per second. So let's draw ourselves carefully here, a line up to there. And as we hit the line at 15, we're going to go across to there. So we start at 15, and by using this graph, I can find out it's got that much kinetic energy. How much is that much? That's the next trick to this question. Well, if we zoom in on this scale here, we blow it up a little bit, we've got 6 there. Then we've got 1, 2, 3, 4, 5 boxes. So 1, 2, 3, 4, 1, 2, 3, 4, 5 boxes. So we got 4. And we're looking at this, let's see, it's 2 boxes below. That is our reading. Now you might be able to tell automatically what it is in this little scale, but let's just work ourselves through it, shall we? So how much is 1 box? How much do we go up by that? Trick here is to go, well, hang on a sec, we've got 1, 2, 3, 4, 5 boxes, and we've got a gap of 2. So we've got a gap of 2, and we're going up by 5 boxes. So 1 box is going to be 5 over 2, which is 0.4. He says running out of room in the corner there. So each box is going to be 0.4. Let's just double check to make sure we've done that right. So if that's 4, this is 4.4, this is 4.8, this is 5.2, that's 5.6, and that's 6.0. So it all matches up, we're away. So we know the kinetic energy at 15 it starts with. So let's have a look here. So 15 meters per second gives us a kinetic energy of 5.2. Now a little note here. They've thrown this a little bit in just to make sure you're paying attention. Kinetic energy of moving air in lowercase k, capital J, kilojoules. So that is 1,000 joules. So that's how much energy it's got to start with. It drops to 13 meters per second. So how much is 13 meters? How much kinetic energy is 13 meters per second? Well, let's have a look on this bottom scale here. Where's 13? Well, we could put a number. It's going to be somewhere around here, but let's make sure we get it right. We're going to do a similar thing to what we did here, just on the vertical scale here. Now we've got 10 here. And if we look, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes till we get to 15. So we're going to do it. So the question is, how much is one box? So we've got a total of 10 boxes. We've got a gap of 10 to 15, which is a gap of 5. Come the way round, gap of 5 over 10 boxes. So each one box is going to be 0.5. So if I look here, if I want the gap to 13, that's going to be a total of 6 boxes here and 4 boxes there. So I can either count 6 this way or 4 that way. I'm going to go 4 this way. 1, 2, 3, 4 there. I'm going to mark that 13. I'm going to do a vertical line up to the line, there we go. And let's do a line across. Now let's pay really careful attention here. And I reckon that's bang on 4, which I think is going to make that maths slightly easier in a minute or two. So at 13 meters per second, we've got a kinetic energy of 4.0, again, kilojoules. So that's the kinetic energy before and afterwards. That's the first stage of this question. If we've gone from 5.2 to 4.0 kilojoules, how much kinetic energy have we lost? Well, if we take these two away from each other, we've got 1.2 kilojoules of energy, which is 1,200 joules. So that's how much kinetic energy has been transferred to the turbine. So that we've lost that amount of kinetic energy, but that's just been transferred from the kinetic energy store of the wind to the kinetic energy store of the turbine, as the turbine is now spinning around. Is that our final answer? I'm afraid not. The percentage of kinetic energy is transferred. So how much? What's this as a percentage of how much we started with? So 1,200 over 5,200. Oh, I'm not going to try that, Mike. That's like a job for the calculator. 1,200 divided by 5,200 is going to be, so 0.2307 la da 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 da. Also, we could have used just these numbers in kilojoules. You'll note that 1.2 over 5.2 is going to be the same answer, 0.2307 la da 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 da. So this is it as a percentage. The total that we lost divided by the total we started with to give me a percentage. We could use it, we could leave it as that, as a decimal, but you notice that the question has asked it as a percentage. So let's times that by 100%, and we're going to get 23% as our final answer. The exam board do allow an answer anything in the range to 18 to 32%. So if you're anything in that range, you would have got the marks as well, just depending on how well you read the scale.